In 1975, a Soviet spacecraft landed on the surface of Venus and began transmitting camera data back to Earth. The first numbers arriving from the probe immediately confused the scientists monitoring the signal. The brightness values were far higher than expected. According to the atmospheric models used at the time, the surface of Venus should have been extremely dark. The planet is covered by a global cloud layer roughly 20 kilometers thick, composed primarily of sulfuric acid droplets suspended in dense carbon dioxide gas. Beneath those clouds sits an atmosphere nearly 90 times denser than Earth's. Scientists assumed that sunlight entering this environment would scatter repeatedly through the thick atmosphere until very little remained by the time it reached the ground. If a probe ever reached the surface, the expectation was that it would be operating in near darkness. However, the brightness measurements from the Soviet lander did not match this prediction. They indicated that the surface was illuminated. At first, the engineers suspected a malfunction in the instrument. The lander carried halogen floodlights designed to illuminate the ground in case the surface was dark enough to prevent photography. One possibility was that the camera was detecting reflected light from its own lamps. However, the floodlights had not been activated yet. The light was coming from the environment itself. This meant that the probe had discovered something that contradicted decades of atmospheric assumptions. Sunlight was reaching the surface of Venus. The spacecraft responsible for this measurement was Venera 9, part of a series of Soviet missions designed to land on Venus and study the planet directly. By the early 1970s, engineers already understood that reaching the surface of Venus required an entirely different approach to spacecraft design. The atmosphere was both extremely dense and extremely hot. Earlier probes had been destroyed long before reaching the ground, either by crushing pressure or by temperatures exceeding the limits of their electronics. To solve this problem, Soviet engineers abandoned conventional spacecraft structures. Instead, the Venera landers were built around a spherical pressure vessel made from thick titanium. A sphere distributes pressure evenly across its surface, which makes it the most structurally efficient shape for surviving extreme compression. The same design principle is used in deep-sea submersibles. Inside this pressure vessel were the probe's electronics, batteries, transmitters, and scientific instruments. The structure was designed to withstand pressures approaching 100 atmospheres. Even with this protection, survival on the surface would only be temporary. The temperature on Venus averages around 475 degrees Celsius. At this temperature, standard electronic components fail rapidly. The landers therefore relied on heavy insulation and internal cooling systems to delay the heat entering the pressure vessel. These systems did not stop the heating process. They only slowed it. The engineers estimated that a successful lander would remain operational for roughly 1 hour before the internal temperature became too high for the electronics to function. Every scientific instrument had to complete its work within that window. One of the most delicate instruments on board was the camera. Traditional cameras rely on lenses and large optical windows. On Venus, this posed a structural risk. A large glass window would weaken the pressure vessel and could potentially crack under the external load. To avoid this problem, the Soviet engineers designed a different imaging system. Instead of taking photographs directly, the device measured light intensity and reconstructed an image from those measurements. The instrument was called a telephotometer. Behind a small cylindrical quartz window, a rotating mirror scanned the horizon slowly. The sensor measured the brightness of each small point in the scene and converted that measurement into a digital value. The probe transmitted these values to Earth as telemetry. Ground computers later reconstructed the scene line by line. The system was simple and mechanically robust, but it had one major limitation: it was slow. Completing a full panoramic image required roughly 30 minutes of continuous operation. If the probe overheated before the scan finished, the resulting image would remain incomplete. The engineers accepted this risk. The priority was reliability rather than speed. On October 22, 1975, Venera 9 successfully survived the descent and landed on the surface of Venus. Shortly after landing, the protective caps covering the camera windows were ejected using small pyrotechnic charges. The telephotometer then began scanning the surrounding terrain. At the same time, the probe transmitted brightness data that immediately attracted attention. The readings indicated that the surface was far brighter than expected. When the first panorama was reconstructed from the telemetry stream, scientists were able to see the landscape clearly. Large rocks covered the ground in irregular shapes. The horizon was visible in the distance. The atmosphere did not appear dark. Instead, the lighting resembled a cloudy afternoon on Earth. The explanation for this observation involved the behavior of light inside a very dense atmosphere. Although the thick Venusian clouds block most direct sunlight, the atmosphere scatters incoming light extremely efficiently. The light is redistributed throughout the lower atmosphere rather than being absorbed completely. The result is a diffuse glow that illuminates the surface from all directions. Strong shadows are rare, but the overall brightness is sufficient for imaging. The discovery showed that the surface of Venus was not the dark environment that earlier models predicted. 3 days later, a second probe, Venera 10, landed approximately 2,000 kilometers away. Its camera returned another panoramic scan of the surface. The terrain at this landing site looked significantly different from the first. Instead of jagged rocks piled around the lander, the ground appeared to consist of flat, plate-like slabs resembling cooled lava flows. This indicated that Venus possessed multiple geological environments rather than a single uniform landscape. The brightness measurements from the second probe confirmed the earlier results. Sunlight was reaching the surface. The earlier assumption of near total darkness had been incorrect. 7 years later, the Soviet Union launched the most advanced Venus landers in the program, Venera 13 and Venera 14. These probes carried upgraded versions of the telephotometer, capable of capturing color information. Instead of performing a single brightness scan, the system repeated the scan multiple times, using red, green, and blue filters. The resulting data sets were later combined to produce full-color images. When the reconstructed panoramas from Venera 13 were released, the appearance of the landscape surprised scientists again. The surface was dominated by deep orange tones. The sky appeared orange, and the rocks appeared orange. To confirm the accuracy of the colors, the probe carried a small calibration panel with strips of white, red, green, and blue paint. In the transmitted images, the white strip appeared orange, and the blue strip appeared almost black. This effect was caused by atmospheric filtering. The dense Venusian atmosphere absorbs a large portion of the blue and green wavelengths of sunlight before they reach the surface. Longer red and orange wavelengths penetrate more effectively. As a result, the entire landscape is illuminated primarily by light shifted toward red. The Venera 13 lander remained operational on the surface for approximately 127 minutes, the longest survival time achieved by any spacecraft on Venus. During this time, it completed several additional experiments. One of these involved an onboard microphone. The microphone was designed primarily to detect atmospheric disturbances and possible electrical activity, and it also functioned as a general audio recorder. The instrument captured the first sound recordings ever made on another planet. The audio revealed a low, continuous noise produced by wind moving slowly across the lander structure. Although the measured wind speed was relatively low, the atmosphere's density increased the aerodynamic forces acting on the probe. The recording also captured the sound of the lander deploying a drilling mechanism used to collect a soil sample. The microphone recorded both the pyrotechnic charge used to activate the drill and the grinding noise of the drill bit cutting into the surface rock. Today, the photographs taken by the Venera missions remain the only direct optical images ever captured from the surface of Venus. Later spacecraft mapped the planet from orbit using radar systems capable of penetrating the cloud layer. These missions revealed enormous volcanoes, lava plains, and tectonic fractures across the planet's surface. However, no camera has returned to the ground since the Venera program ended in the early 1980s. The closest planet to Earth remains visually unexplored at ground level. Our understanding of the Venusian surface still relies on a small set of panoramic images transmitted by Soviet landers that survived only a short time before the extreme heat destroyed them. And one of the first discoveries those machines made was that the surface of Venus was far brighter than scientists once believed.